All right, this is the last worksheet you have to work on. This is 4.5, an optimization. And I will say that there is something I didn't do in 4.3, and that's just because, we're doing this whole at-home thing, so I was trying to make it a little easier. But 4.3, just as a little review, if you do the second derivative, like you do the first derivative, where you set up a number line and then you have this number and you get plus, minus, minus, something like this. This will tell you concavity. Now, concavity is the way that it curves. So if it's a negative, when you plug a test number into the second derivative, you're going to get a curve that's downward, like this. And if it's a positive, when you plug in a test number into the derivative, you're going to get a curve that's upward, like this. So the concavity, this is called concave down and concave up, concave down. So where the concavity changes are called inflection points. Inflection points. And you have to plug those x values back into the original to find the y values to go with them because they're points, right? All right, so this is something I didn't talk about, and I wish I had, but, trying to make it a little easier on you. We don't have to deal with this in 4.5. I was just, wishing I had told you that stuff or done some problems on it. But optimization is, again, word problems. Like related rates, we have to have a process to take care of these word problems. And the one thing I like to do is I like to draw a picture. So number one, we have a thin piece of cardboard that's 30 by 30. So it's a square. Try to draw a square. You know how it is. Drawing a square freehand might not be a square. I don't care. All right, but it's 30 by 30, so I'm going to label this, 30 inches. Oops. Okay. And then this is also 30 inches, so I can do that. And the cardboard itself isn't changing, isn't expanding or shrinking over time, so this isn't related rates. But what optimization does is it says, hey, here's a situation. How can I have a maximum volume or a minimum cost or a maximum area? And that maximum or minimum is telling you what equation you want to take the derivative of. So in this case, it says what dimensions will yield a maximum volume. So what we're doing is we're creating a box. And the volume of a box is length times width times height. It's for a box. So we want to take the derivative of this, but not with implicit. We're going to take this like a normal derivative, no dx dt or dl dt BS. Instead, what we're going to do is we're going to try to figure out how we can put these three variables as one variable. And that's the name of the game with optimization, making more than one variable look like one variable. So in this case, it said, I'm going to cut square corners out of the sides. I'm going to cut squares out of the corners so that I can create sides. And this is me drawing the squares that are cut out. And they're all the same size. So that when I fold this along the dotted line that I'm creating right now, it will create a box, a rectangular box, or actually a square box, square base box. But the cut, I don't know. I don't know how much I cut. That's the answer I'm trying to figure out. How much did I cut so that when I fold up the sides, it creates a box with maximum volume? So this guy's X, and this guy is X, and this guy is X, and this guy is X, and so on around the box like this. They're all the same size. Because I'm cutting square corners, the sides have to be the same. And they all have to be the same size, or else this won't fold into a box. It'll be a weird thing. Anyway, so the new length, the length across here is going to be 30 minus these two x's. And the width is also going to be 30 minus those two x's. And the height is going to be this little distance, x. So my new volume formula is going to be 30 minus 2x for length, 30 minus 2x for width, and then just x for height. And once I FOIL that out, that's 900 minus 60x minus 60x plus 4x squared. I'm going to multiply that by x. I'm going to distribute. And my final volume equation is going to be 900x minus, I'm going to add those two, you get 120x squared. Remember, I'm distributing the x into these. And then plus 4x cubed. So that's my equation. That's the one I like. Now, the thing about this is once I find this equation, then it becomes anything like 4.3, but with first derivative. So take the derivative, and that's 900. That's multiply down to get 240x, and then multiply down to get 12x squared. And then I'm going to set it equal to 0. So what I'm doing is I'm finding critical points so that I can see if it's a max or a min. And I want the one that creates a maximum volume. So solving this is like solving a quadratic equation. I could factor, I could use a quadratic formula. You could use a app at this point since you're at home, right? And I think 12 goes into all of this. Let me pull up my calculator. Sorry about that. Not very good. I'm not very good with Australian accents. I don't know why. It just doesn't come to me very easily. Yeah, it goes in there. So I factor out of 12. I'm going to reverse the order of these. X squared minus, and this is 20x. And this, 900 divided by 12 is 75, right? Okay. Now I can factor this, hopefully. I need two numbers that multiply to give me 75, but add to give me 20. And that is 15 and 5, I believe. So when I'm setting all of them equal to 0, this one's no good. This one gives me x equal to 15, which is also no good. And I'm going to tell you why. If you go back to the original problem, which is why I draw a picture, if you were to cut 15 off of this side and 15 off of this side, you just cut the whole thing. Basically, you cut this whole strip, and you cut this whole strip, and you're just left with a square. You have no box. It's just a square that's smaller. So 15's no good. So that means that this one has to be the right answer, and it is. X equal to 5 inches, since we're all in inches, is going to be the correct x. Now we can answer the question. And the question was, what dimensions will yield a box of maximum volume, and what is the maximum volume? So now that we know this is the idea of what we're cutting out of each side, I can say, okay, the length and the width are both equal to 30 minus 2 times 5. So length is equal to 30 minus 2 times 5. That's 10. 30 minus 10 is 20 inches. And the height is x. So I found that. That's 5 inches. Okay? So that is answer to question number 1, the dimensions, length, width, and height. And then answer number 2 is find the volume. Well, that's length times width times height. So we just say 20 times 20 times 5 is 400 times 5, which is 2,000 cubic inches. Yeah, 400 times 5. Yeah, okay. There you go. That's number 1. And look, that took up like my whole page almost. That's okay. I'll try to do number 2 a little bit smaller. I'll fit it. It'll be fine. All right, number 2. A company's constructing blah, 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 open top, square base, rectangular metal tank. So again, here we have, if we want to draw a picture of this, what I would do is I would draw, it's a square-based open top rectangular, so the sides can be rectangles if you want. But then I'm going to draw one that's slightly up and to the right of that rectangle that's the same size. And then I'm going to connect it with these lines, right? And that creates, a 3-dimensional looking box in a 2-dimensional plane, in case you've ever wanted to do that. Okay, now, me drawing a picture is just what I like to do. Let's see what they tell me about it. They say that the volume is going to be, and like here, With this picture, all the numbers they gave me, I could put on the picture. But in this one, I can't put volume in that picture unless you want to put a number inside, and then it's kind of confusing. So I just write it underneath like this, 67.5 feet cube. And that's all they give you. That's it. Now they did tell you a couple of things that matter. So first of all, anytime you have a picture and it doesn't have numbers on it, like this one, the squares that I cut out, I didn't have a number for that, so I put X, right? Well, we can do that here too. I don't know what the length and width of the square base is, so I'm going to call that X. Okay? Remember it said a square base, so the two sides on the bottom have to be the same. And then the height can be something else. I'm going to call it H because, you know, I don't know what it is. So this is me labeling my picture according to whatever letters I want to and using the information that they gave me. So the idea is that they want to maximize, or they want to minimize surface area, so that the thing that they want to take the derivative of is surface area. Now it's open top, so there's no top here, but there are 1, 2, 3, 4 sides and a bottom. So we want area of all of them added together. So the bottom is going to be x times x plus, and then x times h plus x times h plus x times h plus x times h. So it's 4 sides, and it's always x times h because they're rectangles, right? Length times width. And there we go. There's the equation that I am going to want to take the derivative of. Now, the problem here is that h and x are both in this equation, and I'm not doing implicit, so I don't want this to happen. I need to make h be written in terms of x or vice versa. And that's where this comes in. So the volume of this is actually x squared times h, right? Length times width times height. So x times h is equal to 67.5, isn't it? So what I can do now is I can make h in terms of x just by dividing both sides by x squared. So now I have h is equal to 67.5 over x squared. So that's the name of the game when it comes to optimization, is finding a way of rewriting the original variable or variables in terms of one variable. And usually there's a second little equation that we're dealing with. So the main equation is always what we're going to take the derivative of, and they say maximum or minimum usually. And then the other equation is going to be whatever they gave you. So here I'm going to replace h with this thing. And so that'll give me a is equal to x squared plus 4x and then 67.5 over x squared. And I can clean that up before I take the derivative. X squared plus 67.5 times 4 would be, what is it, 125 times 2, which is 250. Over x. See 1 and 2, so they subtract and you get -1, and it comes down here. Sorry if that's quick, you know. All right, so here we go. This is my equation. I put a little bubble around it. I like it. I like that guy. Now I'm going to take the derivative of it. Derivative of x squared is 2x. Lovely. And this guy is actually 250 x to the -1, so I don't have to do quotient rule. So I'm going to multiply down. I get -250. Then I'm going to subtract 1, I get negative squared. Okay, and then I can change it back into this, 2x minus 250 over x squared equal to 0. Oh, you're not seeing that. There we go. Okay. Now, if I've got a rational in an equation, the way that I get rid of it is multiply everything by this common denominator. He's the only one, so let's just go ahead and multiply everything by x squared. And what will happen is I get 2x cubed for the first one, and then the x squareds will cancel, minus 250. And then 0 times anything is still just 0. All right? Add 250 to this side. Oh no, I'm going to run out of room. Oh. Divide by 2, I get x cubed is equal to 125, and then I take the cube root, and that gives me x is equal to 5. All right. And again, x goes back to this. That is one of the dimensions. Now let's see what they asked for. They said, what dimensions yield the minimum surface area? So that's one of the answers. So length, or x, is equal to 5 feet, because remember it was originally feet cubed. And then h is the other dimension I need. And how in the world am I going to find h? Well, I'm going to plug 5 into this. So h equal to 67.5 divided by 25, which is 5 squared. It's going to give me whatever h is. I don't know what that is. Let's break out the calculator again. 67.5 divided by 25 equals 2.7. And I put a little box around it, and I'm done. Because they didn't ask me for the minimum surface area. They just wanted the dimensions. So, yeah, that's the idea. So there's a lot of pieces to this, and keeping it straight can be difficult. So remember, draw a picture, label what they give you on the picture, or if not, just give it a label like this. And then write the equation of what you're minimizing or maximizing. And then if it has an extra variable, then go back to another equation and try to replace h in terms of that variable, that other variable, like I did here. Once you do, clean it up, take the derivative, set it equal to 0, and solve, and then answer the question. Woo. I know, it's a lot, but you know, you guys are in Cal 1, and this is the very last thing to do, so I believe in you. All right. Private shipping company will accept a box, blah, blah, blah. And they give you a picture. Oh, that's nice. Let me see if I can recreate it here. How'd they do that? Okay, they did like this. And then they went down. And they did like this. Down, connected to this side. And then we're going to do it like this. Okay. And then they went right underneath this line. And then they went like this. And then oh, that was not that fun. Okay. Then they did a bold thing along here to try to give you a sense of a cross section, cutting it right in the center. So this box is not like this, but it's like this, and they cut it right in the center, or somewhere around there. It's not right in the center. Now, they didn't give you numbers for this. They said that the sum of its length and girth does not exceed 90, which we'll talk about that in a second. So since there are no numbers to put on this box, I'm going to give letters. And I have length, which is L. If you don't want to do cursive L because it looks weird, just, L. And then that's it. They said girth, which is the distance around here. So I need a letter for this, and they don't give me a letter, so I can call it whatever. I'm going to go back to, I don't know what, X? Because this is a box with a square end. So this is X and this is X. This is supposed to be a square end. I just didn't draw it very well. Okay, so they want to find largest possible volume. So volume is what we're looking for, length times width times height, right? It's a box, a lot of boxes. And what they gave me was that the sum of its length plus its girth does not exceed 90. So we're trying to maximize it, so let's set it equal to 90, okay? Since this has to be the biggest box possible. So the length plus girth is equal to 90. Let's say girth is actually x plus x plus x plus x, right? It's the distance around. So the girth is actually x plus x plus x plus x, or 4x. All right, that's just me writing out the other bit of information they gave me. Let's go back to this. Now we want length, width, and height. My length is L, right? Keep it at L, maybe? I don't know. My width is x, and my height is x. So this is L times x squared. All right, so far I've went from 3 variables to 2. That's nice, but I need to get rid of this L. So I'm going to go back over here, and I'm going to subtract 4x from both sides to get 90 minus 4x like this. Now I can replace L with this thing, 90 minus 4x in parentheses. All right. So this is very similar to the last problem. You have a problem where you want to minimize or maximize an equation, but it's got too many variables. So you go to the other information they give you and you rewrite one variable in terms of the other so that you can replace it like so. Now I'm going to clean it up before I take the derivative. Always a good idea. 90x squared minus 4x cubed. And now I'm ready to take the derivative. That's my guy. You don't have to put a bubble around your final equation before you take the derivative, but I like to. For some reason, it tells me I came to the end of this step. Now I'm going to do the derivative step, which is multiply down, get 180, subtract 1, you get x. Multiply down, you get 12, subtract 1, you get x squared. And I'm going to set that equal to 0. Now this is quadratic, but I have a GCF, don't I? Let's see, does 12 go into 180? Yes, it does. Yes, it does. So 12x is your GCF. And if you divide both by 12x, you will get 15 minus x. All right. So this gives me x equal to 0. The 12 doesn't mean anything, but the x equal to 0 is an answer that I get by solving. And x equal to 0 means I don't have a box at all. So that's no good. And then this one will give me x equal to 15, and that's the one I want, right? But that's not answering the question. This is just getting to that x value that will help me answer the question. The question is what dimensions again? So they want length and width and height. So let's plug 15. Well, actually, that is one of the dimensions. X is equal to 15. So we say x is equal to 15, and this is inches, right? Yes, inches. And then I'm going to plug 15 into here to get my length, 90 minus 4 times 15. And that's 60, so 90 minus 60 is 30. Now will give me a maximum volume. Okay? All right. So that is a lot of, so the box problem is one that you will definitely see on the quiz. 2 of those box problems. I like this one better than the previous one, and that's because the previous one has the negative exponent business. I don't know. But both of them, you know, are good problems. This one is a wall, and you need to find the shortest beam that will reach this to the side of the building from the ground outside the wall. So there, okay, so there's a wall in a building. So let's just draw this picture again. Here's the wall. Here, no, that's the building. I'm sorry. This is the wall. And this is the ground. And you're going to put a beam down like so, so that it leans up against this 10-foot wall, which doesn't change. So I can go ahead and put that number on there. I don't know how far up the building we're talking about. I don't know how long the beam is. But I do know that the distance between this wall and this building is 33 feet. Okay. And what they want to know, and that's all of the numbers that they give you. So there's no extra little number stuff to put down. But they say, find the length of the shortest straight beam. So they want to shorten this guy. So let's call this something. Let's call this B for beam. Capital B. Let's do that. Okay? That's the beam. Now, how do I find the length, the distance of this beam? Well, you can use the Pythagorean theorem, can't you? Yes, you can. Or there might be another one. No, there's, I mean, we'll talk about it. So I'm going to probably do the Pythagorean theorem here. So I'm going to have this side that I don't know how high it's going to be. So I'm going to call it H. And then I don't know what this distance is here, so I'm going to call this x, okay? All right, so they want to minimize the beam, and that's going to be the square root of this side squared plus this side squared. So x plus 33 squared plus h squared. Okay. Okay. Okay, so now what I need to do is I need to get h in terms of x or x in terms of h. And there's this other equation you can do with this. And if you remember related rates, you might be seeing it. It's similar triangles. So the idea, though, is that I've got to figure out how to relate this little triangle to this big triangle. And that is this side goes to this side. So 10 goes to h, as this side, this little x, goes to the long side, which is x plus 33. Right? That's how we'll relate with similar triangles. This is the extra stuff that I can use to figure out how to get h in terms of x or vice versa. Now, if I remember my similar triangle proportions, I cross multiply, right? So I get 10 times x plus 33 is equal to hx. And, it looks like it's going to be easier just to get h by itself here, so I'm going to divide by x. And now I have h in terms of this thing, which I can't really simplify. I mean, I could distribute, but I don't want to. And I'm going to show you why in just a second. Okay, so this guy is going to replace this guy, and let's do that. And by the way, I'm seeing the square root. Instead, I'm going to make it to the 1/2 power in just a second. All right, so we got x plus 33. I'm not changing him. And then I have this thing, which is 10 times x plus 33 over x. That's squared. And the whole thing's to the 1/2 power. And you might be like, oh my gosh, Mr. Ernest, what are you doing to us? And yeah, I know. I'm not putting this one on the quiz. I'm not putting it on the quiz. Anyway, I just wanted you to see it. So if you want to simplify this before you take the derivative, which I believe you do, you kind of want to, let's get that 2 power to all of these things. And let's see, this is x plus 33 squared plus 100 times x plus 33 squared all over x squared to the 1/2. And now that you can see that these two terms both have an x plus 33 squared in it, you can factor it out. X plus 30, I'm sorry, this is all still in that parentheses. And then x plus 33 squared is out, and now that leaves you with 1, and that leaves you with 100 over x squared to the 1/2 power. All right, so the cool thing here is that once you factor like this 1/2 power will go to both. And that means that this is just x plus 33. And then this guy will be, let's clean this up, x squared plus 100 over x squared to the 1/2, right? If you make this x squared over x squared, you can add them like this. And then you can take the square root of the top and bottom here, and this becomes x. So this becomes x plus 33. And this is x squared plus 100 to the 1/2 power. And this is all over x. Woo! Oh no, you're not even seeing it. Okay, there you go. So this is the idea. And if we want to take the derivative of this, it's going to get mighty nasty, right? It's going to get ugly. And that's because you got multiple things being multiplied. You got multiply and divide. You got a quotient rule and a, So, I don't know what you want to do. What do you want to do? Do you want to put this x with him? Do you want to put it with him? I'm going to put it with him. See, this x goes to one of these since it's times and not plus. So let's clean this up one last time, and let's divide the x into x plus 33, and we'll get 1 plus 33 over x, and that'll be times x squared plus 100 to the 1/2 power. So now this is just a product rule with a chain rule involved, and it's not awful, but it's ready, I think. That's as much as I'm going to do to it. Woo! Algebra is fun. That's why this one's not on the quiz. Anyway, so I'm going to multiply. This guy, derivative is going to be negative 33 over x squared times x squared plus 100 to the 1/2 power. And then plus this guy without being taken derivative of, so same thing. And then 1/2 that thing to the negative 1/2 times 2x. Okay, so if we're going to solve this guy, I'm going to need more paper. So let's just do this little trick. No, okay. Get over there. All right, so we're going to set this equal to 0 now. And let me just clean up a little bit, show you what I mean. So the 1/2. And then this 1/2 and this 2 will cancel, and you'll be left with x times 1 plus 33 over x times x squared plus 100 to the negative 1/2. So when you have this equal to 0, and you want to solve, you want to factor this. And you can pull out a x squared plus 100 to the negative 1/2 power. What that does is when you divide, this will give you negative 33 over x squared times x squared plus 100 to the first power. Because 1/2 minus negative 1/2 is 1. So we're dividing. And when we divide, that just cancels. So we're left with x times 1 plus 33 over x. Is this the quickest way to do it? Maybe not. I don't know. You'd have to show me a quicker way to do this problem, maybe. All right, so setting this equal to 0 means that, I'm going to clean this up a little bit. Distribute, and you get negative 33, and then minus 3300 over x squared. Distribute, and you get x, and then the x's cancel plus 33. And that's all over the square root of x squared plus 100. And since we're setting it equal to 0, which is where I was trying to go with that, this denominator set equal to 0 is not going to give you anything because there's nothing you can square that will add to 100 and be equal to 0, right? It's always going to be positive, so it'll always be bigger than 100. It'll never be 0. So this doesn't even matter. It's this stuff up here that does. By the way, negative 33, positive 33. Maybe you saw that. So what you're left with is really negative 3300 over x squared plus x equal to 0 to find any answer that you might have. Again, this is irrational, so we're going to multiply everything by x squared times x squared times x squared. And then we get, cancel, negative 3300 plus x cubed equal to 0. Add that over here. And then take the cube root. So I'm going to need my calculator. 3300, and then I'm going to take the cube root, and it is 14.888. Yeah? 14.888. All right. And I'm going to leave this like that. I could have all these decimals that come after that too, but I'm going to try to answer the question. I'm going to add this to my memory. All right, let's see. It says, find the length of the shortest straight beam. So going back to the original problem, they want B. Well, I need X, and I found it, and I need H, but I can find that here. I just need to plug X into this, right? So if I want H, I would say X is 14.888. You can even say 15 if you really want to. What do they say? They don't even say how many decimals. So if you want to, make it easier on yourself and say this is 15, let's go back. Let me say X is 15. That's fine. So this becomes H is equal to 10 times 15 plus 33 is 48, right? Over 15. That's 2/3 of 48. So we got 480 divided by 15, and that's 32. Hey. So we got the X is 15, H is 32, and if I want to deal with finding the size of the beam, let's go over here. It's one big triangle. I'm going to forget about the little one now. Because X being 15 and 33, they'll add to give me 48. And then this guy is 32. So now I can do Pythagorean theorem, which says 32 squared plus 48 squared is equal to b squared. So let's do that. 32 squared, 1024. And then 48 squared, 2304. Add them, 3328. Now I'm going to take the square root, and I get 57.7 feet, right? We're dealing with feet. Oh, I can't wait to check this answer. Please be right. Yep, okay. Woo! That was a hell of a problem, wasn't it? Not on your quiz. Okay, great. Glad we had that talk. All right, now let's do number 5. So yeah, so fast forward if you really don't want to know about all that junk. So we got a rectangular wooden beam, and it's proportional to its width, blah, 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 blah. Hey, they drew a picture. All right, so let's draw a little rectangle. You know, that's basically how my mind works when I see a word problem. I start it, and then I'm like, no, I'm out. Okay, so I'm going to do a little dotted line here, which I need to figure out what that is. It says 10-inch diameter, so I think this is 10 inches. Cylindrical log, yeah. So there's a circle here that's dealing with diameter, so that's 10 inches. And they label this D, which is not diameter, it's its depth. So D for depth. And then W is its width. Okay, that makes sense. Okay, and then they just tell you that the strength, well, okay, before that, let's say the dimensions of the strongest beam. So they want the maximum strength. And they give you that. They say the strength is proportional, so is, to its width times the square of its depth. Square of its depth. So it's proportional is saying that as this thing goes up, this goes up, okay? I have a feeling I'm going to screw this up. All right, so I haven't done this before, and that's okay. So we got 10 inches along the diameter here, and we got W and D, and I need to figure out how to get W in terms of D or D in terms of W, because this is the equation I want to take the derivative of. So I guess looking at this, you see a right triangle, and that uses a Pythagorean theorem. So let's go with that. W squared plus D squared is equal to 100, 10 squared. Oh man, you know what? Let's make D squared be the one I'm replacing, because that would mean I would just replace this. If I made W in terms of D, I would have to put a square root in here, and then I'm taking the derivative with a thing that has a square root, and that's no fun. But instead I can do it this way. I can say W times 100 minus W squared. And oh, that's so much nicer, isn't it? Distribute to clean it up. 100W minus W cubed is your guy. And you're like, oh my God, Mr. Ernest, this is way nicer. And I'm like, yeah, I know. I could still be screwing this up, though, by the way. I'm just going to say this right up in our front. All right, S prime is 100 minus 3W squared. I'm going to set that guy equal to 0. So that means bring 3W squared over here, positive, divide by 3, and you get 100 over 3 equal W squared. And so your width ends up being 10 over the square root of 3. Now we only want the positive one because this is a real life problem. Okay, so that's the width, and it's asking me find the dimensions of the strongest beam. So I found one of the dimensions. Width is this, and I can write it. It says round answers to the nearest tenth. So let's do that. Let's clear U. Let's say 3 square root. Let's add that to the memory. And then I'll say 10 divided by memory recall. And that's 5.8, nearest tenth. And this is in inches. There's one of my answers. The other one is d, so let's say what that is. D squared is equal to 100 minus w squared, which is 100 over 3. Okay, so this is 300 over 3 minus what's 200 over 3. And then I'm going to take the square root, and I'm going to get, let's see, 200 divided by 3. And then square root of that is 8.16, so 8.2 inches. Please be right, please be right, please be right. 5.8 and 8.2, yeah. So when they said proportional, it was throwing me off, but I think it's because they're talking about the circular beam versus the rectangular wooden beam. So it's, proportional in that way. But anyway, all right, so number 5, that was number 5. Number 6, if the price charged for a candy bar, blah, blah, blah. Oh, look, there's a formula. P of x is equal to 141 minus x over 28. All right, so I wrote that out. And this is the P, which stands for price. This is the price. And x is the number, is 1,000 candy bars. And so maybe you want to write that somewhere or just keep the thing up. How many candy bars must be sold to maximize revenue? Okay, so something about you need to know is that revenue is the price that you're selling times the number that you sell. It's that simple of an equation. And this is the one we're going to take the derivative of. I have an equation for P that's in terms of x, and then I have x. So everything's given to you basically in this problem, which makes it a great candidate to go on the quiz. There you go. So we're just going to replace P with this thing, and there you go. Distribute to clean it up, and I get 141x minus x squared over 28, right? Now, that's my equation. I'm going to take the derivative. R prime is equal to 141 minus, multiply down, you get 1 over 14x equal to 0. So like this thing is actually 1 over 28 x squared, and so when I multiply down, it's 2 over 28, which reduces to this. In case you were wondering what in the world. All right, so to solve, I move this over here, or I can multiply everything by 14. I like that. So that gives me 141 times 14, which I can't do in my head. 141 times 14, it's 1974. And then these 14s cancel x. And oh look, x is equal to 1974,000. Because that was what x was in terms of, 1,000 candy bars. So 1,000 is actually 1.974 million candy bars. In case you were wanting to put that in terms you understood. They actually wrote 1,000,000, which is, I don't know, silly. Sorry, there you go. Okay, and then we got number 7 and number 8, last two. Number 7, we have a rectangular field. It's enclosed on 4 sides with a fence. So we can draw a rectangle here. That last one we couldn't draw because it was revenue. It's not really a picture to go with that. So 4 sides to the fence, and then we have fencing costs. But they didn't tell us anything about that. So they said like it's $4 per foot on 2 opposite sides, and it's also $8 per foot on the other 2 sides. So it doesn't matter which one you pick. Like the rectangle can look like this, or it could be a skinnier rectangle. But if you're wanting to minimize cost, which is, they say, the cheapest, so that's minimizing cost, then this is probably the $4 one. So I'm going to call this X, I'm going to call this Y. You can call it length and width if you want. But basically what we're going to say is the cost is going to be the perimeter times the amount of money. Or we're going to say $4 times X plus $8 times Y, and then plus another $4 times X plus another $8 times Y. Right? That's how you find cost, is the amount of money per foot times the number of feet. So we can clean this up. Get 8x plus 16y. And we have a problem, right? We can't take the derivative of this because we have two different variables. So now we need something else to help us get x in terms of y or vice versa. And that's what the area is going to be. So they said that the area is 880 square feet. So area is x times y, or length times width. So if I get x in terms of y, I can say divide by y. No, I'm going to say y divided by x. And that's going to give me y equal to 880 over x, which is what I'm going to put right here. So we have 8x plus 16 times 880 over x. Okay. And now I need to clean this up. 8x plus whatever 16 times 880 is. 16 times 880. 14080. And this is over x, but I'm going to write it as x to the negative 1 because I like that better for derivative purposes. Okay, so we're going to take the derivative, which is next. It's 8. Multiply down, we get subtract 14080. What did I even say? To the negative 2. Okay. All right, so I got to make this x to the negative x squared in the denominator is what I'm trying to say. Losing it. And then I'm going to multiply everything by x squared. So times x squared times 0. So it's 8x squared minus 14080 equal to 0. Right? These cancel. Add this to this side. Divide by 8. Divide by 8. 1760. I know. Probably a bad year for colonists. Take the square root, and we get 41.95. I don't know what they want. Let's go to the question and see. Number 7, they say find the dimensions of the field that would be the cheapest to enclose. So if we're going to round this to the feet, because usually fencing is in terms of feet, this is going to be 42 feet. Right, there's one of the dimensions. The other dimensions you'll plug into here, and you get y equal to 880 divided by 42. And then we will get, let's see, 880 divided by 42, and that is 20.95. So that's going to round to 21 feet. All right, those are the dimensions that will give you the minimum cost for this fence. All right, last one, number 8. And hopefully it's not too bad. It's a revenue profit one, so there's no picture to draw. And they give you two equations. They give you that revenue is equal to 20x minus 0.5x squared. And they give you that cost is equal to 4x plus 5. These are the cost and revenue functions. And they say find the number of units to yield the maximum profit. So profit is your equation. And profit is always found by revenue minus costs. So whatever you make minus whatever you spent, that's profit. So we're going to plug those two in for R and C, and this one will only have one variable, which is lovely. So 20x minus 0.5x squared, and then minus parentheses 4x plus 5. Be careful there, because this is actually a whole thing you're plugging in for C. So if we distribute this and we combine this term and this term together, we will get an equation that we can take the derivative of. Negative 0.5x squared, and then 20 minus 4 is 16x, and then negative 5. Put a little bubble. There's my equation for profit. All right. Next, take the derivative. Profit derivative is going to be multiply down negative 1x and then plus 16. Set that equal to 0. Add x to this side and you get x equal to 16. And is that what they want? Let's see. Find the number of units that must be produced and sold in order to yield the maximum There it is. That was the answer. I'm going to put a little box around it now. I did not have anything else to do. All right. All right, so thank you.